Hi, it's Jocelyn. I'm about to do Advent of Code Day 19. Alright, so we have a few scanners, each with probably 3D coordinates. Beacon scanner. The scanners do not know their own positions. Okay, so we're determining the positions of the beacons and scanners. Okay, so they also can be rotated. Okay, and we know that. Okay, so we know that one scanner will have 12 the same beacons of other scanners. Okay, wow, this is crazy. Okay. Well, let's start by parsing. So we've learned this from before. We can do lines dot, I think it's by ref. There we go. So the first line should match scanner 0 or scanner whatever number. We don't actually need to parse it just because each one is incremented by 1. So we can just do lines dot next just to get the next line, and then if lines or the line is empty, then we're going to break out of this, otherwise it's a location. So I don't think there's like a split twice function, so we'll do x, y, z is equal to line dot split on comma dot unwrap. Oh no, there's not dot unwrap. Then we'll say let x is equal to x, y, z dot next dot unwrap. And same for y and z. And that is a point. So we'll say we'll just say scanners is equal to effect.new, and for each scanner, let's see, we'll find the location of the beacons. So that's also effect new. And then we will push beacons x, y, z. Now we need to parse these as well. These are going to be IS64s, and they need to be unwrapped. Okay. And scanners dot push beacons. And eventually we need to break out of this. So if lines dot next dot is none, then we are done. And let's just make sure we parse this correctly. So we print line which I'm going to print. So first of all, the number of scanners, and then also just the scanners. Okay, so here it says that we have 38 scanners, which makes sense because we go from 0 to 37, and the first one is 774 minus 45, 852. So I think that we parsed that correctly. That was the easy part. I think with the first of all we need to figure out how to rotate them. Let's see. Said something about degrees. Okay, so due to magnetic alignment, each scanner is rotated to some integer number of 90-degree turns around all of the x, y, and z axes. gosh, okay, this is going to take a while, and geometry is never my strong point. I'm going to assert here that we have exactly 24 different ones as our nice hint in the example gave us. We do not have 24. How many do we have? $48. Okay. Oh, I see. Because the axes are relative to each other. Oh my god, I just do. My geometry is just like so bad. This is what I want. Okay. Just can't read Python. Okay. Now 26 minutes in, we can actually get our list of rotations. This is pretty great. Okay. Oh my goodness. So for checking every pair of scanners, and then for every pair of scanners, we're checking 24 different rotations. And then we're looking for 12 different overlaps by trying to position them such that there are overlaps. What does that look like? So we have, it says 30, we have 38 scanners. So 38 scanners times, but we need every pair of 2 scanners. So yeah, that's roughly 38 squared, which is enough. So that's 1,444. You can't see my calculations here. I'm just trying to do a back of the envelope calculation. And then for every pair of those, there's 24 different orientations that the first pair could be in. We don't need to rotate both of them, because once we rotate one, the other will have that same rotation. That's 3,000. That's 34,000 or 35,000. And then we need to align them. So each one of these scanners has how many points is that? Let's see a good way of getting this. I'm just going to use word count. I think roughly 26. So for each of these things we're considering, there's 26 squared. And now we're looking at 23 million things to consider in order to find the matching pairs. And once we find the matching pairs of things, once we find the matching pairs of scanners, then we have to reassemble them. So is this practical at all? Yes, this is it is practical to consider 23 million things, I think. Okay, yeah, let's do this. So for scanner in scanners dot iter dot enumerate, we're going to look at all the scanners that come after that one. So for other scanner in scanners, starting at I+1. That should be good. That will be, we'll need to compare the two scanners. So for the first scanner, we're going to look at all the different orientations, and we're going to compare that to the first orientation of the second scanner. you don't need to rotate both of them, is I think the trick there. Rotating one is sufficient to see if it's actually going to work. Okay. Right. This is actually beacons dot into iter. No, I got this. Yeah, I got this. Let's see. I forget how to do this, so for the 24 different directions, we're going to do this. And I'll probably get a clippy warning on how to improve that. And then over here, we're going to do for rotations, or for for point in rotations x, y, z. Then we're going to, I guess, dot into iter dot enumerate. Then we can say beacons I dot push that point. Something like that. And then we can say scanners dot push beacons, and that's what I meant to do the first time. I just wasn't thinking as clearly as I could have about that. Okay. This probably needs to be a reference. Okay, so let's find all of the potential offsets. So this will be, okay, so for, we're doing this again, for I beacon in, actually we don't need the, yeah, we're just getting the list of possible offsets here. So for beacon in beacons, and then for other beacon in beacons, potential offsets is going to be a hash map from the number of, or from the offset to the number of offsets that meet that. So something like beacon dot 0 minus other beacon dot 0, and then the same thing for the other two dimensions. Might make sense to make types for these if we're going to do a lot of this, which I think we might be. So potential offsets dot the entry for that offset, or default, we're going to increment that by 1. And then we should find lots of these that have at least 12 in common. So potential offsets, we're going to say dot into iter dot filter. We're going to filter to see if the count I'll fix that in a second, is greater to or equal than, I think we said 12 in here, is that right? Yeah, 12. And then we're going to map this to, we just care about the offset. And then we're going to collect that into offsets. So let potential offsets now as a vector is equal to that. Need a semicolon. What else do we need? Okay, I'm just gonna give this the I mean, I can probably figure this out, but it's just easier to do. Oh, I see. It's probably easier here to give this potential offsets a type, which will just be a hash map from point to usize, point to count. Wonderful. And this is taking a while, but it does eventually finish. So now we can list our, which is a good sign because that's a lot of the computation we need to do. And we should get some potential offsets. I am suspicious. Oh, what am I doing here? Okay. Of course. Oh my God, look at that. So now we have some potential offsets. So it looks from this just that like potential offsets dot length is either 0 or 1. I'm just going to assert that. So if potential offsets, okay, that's not going to compile. It's not going to compile. Oh, it is. It wants to be empty. Okay, so if let some offset is equal to potential offsets dot, guess we can do pop. Now we know we have an offset and a rotation and 2 pairs. So now we can make a list of scanners that align with each other along with the rotation between each other. The rotation between each other and the dimensions between, or the translation between each other. So here we go. It's probably easier to say scanners dot iter dot enumerate dot skip I plus 1. Because on the first iteration, we want to skip the very first one. This is the same. It just gives us the index of the other scanner. So if we found a match, then we're going to say ij. We need to know the rotation between the 2 of them. So we're going to also do enumerate here. So this fully describes the relationship between those 2 alignments. There we go. Okay. And I want to print that just to see what that looks like. So now that we have all the alignments, it's probably an easier problem to figure out how those all tie together. But I still need to think about how we're doing that. So if we found something that's not at the canonical axis, then I think we need to rotate everything we found so far that's in that universe to match the rotation we just found. So we'll have sets of scanners that we know all have the same system. Okay. So this variable is going to contain sets of scanners that are all in the same rotation. So if k is not equal to 0, then we need to rotate scanner and any of the other scanners in the same system to be in that new system, and then we add j to that system. Okay, that makes sense. So I'm going to make another loop here. And call this outer. And then say if k is not equal to 0, then break outer, which just gets us back into this loop. I'm going to say let mute next realignment is equal to none. And then in this case, I'm going to say next realignment is equal to sum, and that's I and j, and we need to rotate that by k. Otherwise, we can just add to our alignment or our aligned array. Here we're going to check next realignment. Otherwise, we're done. I'm going to panic here just like to make sure that this logic is working, that we're getting our next realignment, and we'll figure out this systems thing in a second. Wonderful. So that's exactly what we expected. So now that we're here, we're going to see if there's already a system that contains I and j. So systems is going to be a vector of hash sets of indices. And so these all have the same rotation. Is that right? Did I get that right? No. Just 2. So just an A element, we want all of the elements. So filter, let's see, items item should contain I or j because it could contain I and j, and that's even harder. So let's get the one that contains I. And the one that contains j. Anyway, it's easiest if we don't have, if system I and system j are both none. So we're going to deal with each of these cases separately. And add them as we need to. So in this case, we're going to rotate I. We are going to rotate I by rotation I. So that looks like scanners at I is equal to, actually we'll say the point, first of all let's find the point. So point is equal to scanners I at rotation of I. And that should be 1 point, shouldn't it? Because scanners is oh no, those are the points. Yes, these are the points at that. Okay. Then we're going to find the new rotation. So rotations is equal to, no, it's the same logic as we did here. Might make a function for this in a second. So this is just making it so the first rotation is rotation I. Something like that. Oops. Except this would now be something like that. And really we could take it like that. This is fine, I think, but it's easier just to like clone it. Okay. This is never going to finish, but we can say we can now insert a system that that contains both of these. So wonderful. So we got past the first part, and now we're at another situation. So let's figure out what the next situation to handle is. So that'll be this. That will be this I and some. Let's see. Yes, some system I, and J does not have a system. Let's look at that one next. Hopefully that is the hopefully that's the next one, because that's the one I know how to, I can just like think about how to solve right now. Line 120, it's not. Okay. Maybe it's this one. It is. Okay, so let's look at this. So I'm curious what system I is, what system J is, and what IJ and the rotation is. Okay, so we're rotating 0 by 9 to match 9. And then we're trying again. And we're saying that now we need to rotate 0 by 11 to match 9. So something is odd here. In our order here, the first one is not necessarily the original. Damn it. I guess the 11th one is. Well, this is super hacky, but I'm going to say that we just swap those two. Does that work? No, it's not that nice. Wonderful. Okay, so that I guess leaves the case where I is not in the system, but J is. And this should be unreachable now. Perfect. oh, no, never mind. It's this one where we're going to have to rotate everything in system I. I think it's worth extracting this into a function. But there's other things going on. Okay. Let's see. So systems. Is there like a find mute? No, there's, okay. There's intermute, but can't get them both at the same time. So we're going to need to enumerate these. Okay. So in this case, we just care about the index of system I. So something like that, we're going to just like insert date into that system after we've rotated everything in system I. So what does that look like? That's for I in system I, we need to do the same thing as we did here. I'm going to extract this into a new function in a moment, but for now I'm just going to do this. Oh, this is super cool. Okay. Explicit panic at line 150. So this is the tricky part. Because J is already part of a system. And I is already part of a system. Oh, actually, no, it doesn't. We still just need to rotate the ones in I in this case. But we do need to, okay, we do need to combine these two systems over here. So, so first of all, let's assert that they're different. And we'll say system min is equal to system I dot min system j, and we have something similar for the max. And then we can remove the max one. And we'll want to add it to the min one. Oh, it panics if it's out of bounds, so. Something like that. And I don't think this case ever happens. Just because j is always greater than I. Well, it does. I'm a bit confused that it happens, but that's not going to stop us. Okay. So similar to the first case, we just need to rotate I. This is a mess. Okay, we just need to rotate I. But instead of pushing, we're just going to say systems at system j dot insert I. And now we should have everything aligned. Oh my god, look at that. And all the rotations are 0. Oh my god, I can't believe we did this. So after doing these rotations, so it's saying, okay, I think we just got the sign here backwards. Great, okay. Now we're just going to continue this. Again, we need to extract this, but I'm going to do that later. It's easier right now just to duplicate it. Oh my god, it's working. Okay, I'm just going to assume this is all working now. Then we can say, we can go back to what we had before, which is scanners equals scanners dot into iter.map rotations, which is the zeroth rotation, dot collect. And this needs to be cloned, and this is going to be a vector. And then for all the points, so for scanner in scanners, for point in points, oh my gosh, it's amazing. Here for point in points, let's see, we're going to insert this into points. And then we're going to return the length of points. Which is a U size. And that is fair. We do not need that 0 anymore. Okay, we might need this example, so I'm going to be ready to use it if I need to. Going to actually just put this in its own file, so example1.txt. But we have an answer, which is 457. And that's right. All right, continuing on to part 2. How far apart do the scanners get? Largest Manhattan distance between any two scanners, rather than points. This is obnoxious because we're moving okay, so we need to keep track of how much we move the scanners. That is super annoying. Okay, I'm going to rename part A to solve. And we're going to calculate them both at the same time. So this is just, so this offset I is what's relevant here. That's the offset, that's the amount that we're moving I. We're not moving J, we're moving I. So we're just going to make a, we're going to make a moved, which is a hash map. And it's going to be a hash map between a point and, sorry, it's going to be a hash map between the sensor number, which I guess is also U size, and the amount that's moved by. So here we're going to move, everything in system I by offset I. So that's just going to look like moved dot entry I or defaults. and we're going to add those two vectors. So e dot 0 plus equals offset I dot 0, and same for 1 and 2. I can add this 457 over here. Oh, wait, these are 64s. Oops. And we'll need this in all the other cases we do this, which is here, here, and here. Okay, that's great. Now we can figure out the movement, the maximum movement between an arbitrary item and the longest by going through this movement array. Is it called movement? Yeah, it's called move. Into iter. Dot max by key, which is going to take, we don't care what the first item, and it's going to take x, y, z, and we want x plus y plus z. That's Manhattan distance. And then you're going to assert that they're the maximum. No, actually, those are just distances. Okay. We're just comparing all of them. So we have max distance, which starts at 0, and max distance is equal to max distance, or the maximum of the distance between these two. P1.0 minus P2.0 absolute value, plus that for the other 2 points, or the 2 dimensions rather. Something like that. And we're going to return that distance as well, which is an I-64. Right, because it's a hash map, not a vector. There's definitely a default for a tuple. All right, so now it's running. It'll just take a while, but hopefully this time we shall get a maximum distance. So this unwrapper default, we could have used just like a vector to store all of the movements, and we need that because whatever the last j is, that one is like going to be at 0, 0, 0, and it's not going to have been moved. So that one, yeah, so that one we don't have an entry for, and that's, I wasn't expecting it to pass. I guess that means that this isn't working. Because that's just tracking what was moved the last iteration. We need to track how the systems moved throughout all this process. Now, most of the reason this is so slow right now is because we are not skipping the ones that we know are already good. We could just continue from where we left off as far as I know. This last case is kind of scaring me, this non-system J. No, it's actually still fine. It means we got to an I and the I is not in the system, but J is already in one. Okay, so that's still fine. So we could continue where we left off, I think, just like as an optimization. But for now, we have an answer. And my answer is too high. Oh, we might need to rotate. Damn it, we're not rotating those points. That is nasty. Okay. Right, of course. Something like that. can't believe it. Okay. Yeah, here we go with the other example. So I think once I'm finished this, I'm just going to go to bed. But there's a few issues still with this. Mainly is that there's two main issues that are just gross. First of all, this should be really its own function. That can be isolated to its own thing. The second thing is this align thing that we're generating. We only need to generate in the last one. Otherwise, we can just skip the first I because that's all aligned. And that would make this run a lot faster. Rather than needing to rerun it whenever there's a rotation. Anyway, we have an answer. That answer is smaller than the previous answer, so I'm optimistic. And we got it right. All right. Wow, this one was hard. This one was long. It was pretty interesting, though. I had a lot of fun with this one. Anyway, see you tomorrow.